Hello, welcome to AP Calculus Lecture 5.6c, where we're going to go over a few more exponential models. Just going to work 3 example problems on this lecture, starting on page 364. So the first one is problem number 40, where we're going through some population data. So it says in exercise 39 through 42, the table gives the population in millions of a city in 1990. And the projected population in the year 2000. Find the exponential growth model. Y equals CE to the KT for the population by letting T equal 0 correspond to 1990. And use the model to predict the population of the city in 2010. And they have a typo there. 1900 should be 1990. So we're going to do Houston, Texas, example 40. Where the population in 1990 is 2.3 million, and the population in 2000 is 2.65 million, and we want to know what is our projection for 2010. So using the model y equals CE to the KT. Okay, so year 0 is 1990. So y would be our projection. Okay, so and then C would be the 1990 population. And we don't know K, but we have enough information to figure out K because we do know what 10 is. So Y is going to be 2.65 million. I'm just going to write 2.65. That's equal to 2.3 million. So 2000 population is equal to the 1990 population times E. We don't know K, but we know that there's 10 years of difference between 1990 and 2000. So times 10. We would expect our K to be positive because population is growing. If population were declining, then K would be negative. So we'll divide both sides by 2.3. And then that would give me 1.152 is equal to E. And we'll reverse these to the 10K. So I'll use take the natural log of both sides. Now I can bring the 10K out front. Natural log of E is 1. So K is equal to the natural log of 1.152 over 10. Okay, you put that in your calculator to get 0.01415. All right, so I went ahead and took that out 4 non-zeros so that we can get a better estimate. So now we want to know what is our estimate in 2010. So we'll call this Y of 20 because in 2010 is 20 years past 1990. Okay, so Y of 20 is going to be the initial population. So we're using this right here, C, 2.3, E, 2.01415. We just figured out K for this model. Times 20. All right, so 2.3 times e to the 0.01415 times 20. If you put that in your calculator, you'll get 3.052 million. All right, so really it's just like all the other problems we've been working. You can use some initial data to find K. And then you can use that to project what you're trying to get with the model. And in this case, that would be time. All right, let's look at number 46. And we're going to go over to page, we're still on 364. So bringing that into view, 46 is about revenue. It says because of a slump in the economy, a company finds that its annual revenues have dropped from $742,000 in 1996 to $632,000 in 1998. If the revenue is following an exponential pattern of decline, what is the expected revenue for 1999? We're going to let t equals 0 represent 1996. Okay, and we're going to continue to use this exponential model. Y is equal to C e to the kt. Y would be our 1998 revenue. As you can see, it's a pretty old book here. And then the initial revenue occurred in 1996. So our 1998 revenue is $632,000. That equals the 1996 revenue, which is $742,000, times E. We don't know K. We're going to figure that out. And then there's 2 years difference between those two numbers. All right, so if we divide both sides by 742,000, let's see. Let's do that here real quick. 632 divided by 742 is 0.8518. Is equal to e to the 2k. So let's take the natural log of both sides. Can bring the 2k out front. So k is equal to the natural log of 0.8518 over 2. And that's negative 0.08023. So it makes sense that k would be negative because the numbers are declining. All right, so I took that out actually 4 spots. The more you take it out, the better estimate that you will get. So if we want to figure out what would the revenue be in 1999, so that's going to be y of 3. So this is y of 2, 2 years after 1996. So y of 3 would be 742,000 e to the minus 0.08. Times 3, right? So we're going to put in 3 for t. We figured out k. And then that is $583,275. Of course, if you rounded more, if you took it out further, or if you truncated it to 0.0802, your number is going to be a little different. But this is a multiple choice test, so you will just need to be matching as closely as possible to the multiple choice answer. But the further you go out, the closer that you'll get. All right, so that's example 2 of 3 we're going to do in this lecture. So the last problem that we're going to work is from Newton's law of cooling. So Newton was a great scientist in the 1600s, 1700s. Is credited with inventing calculus. and he did a lot of modeling. Newton's law of cooling. So he came up with a model of if you heat something up and then you cool it in an environment that has a consistent temperature, you can see how fast it will cool down with this model. So you do not need to memorize this model. The model of cooling would be given to you on the test. But T sub F is equal to T sub S plus CE to the KT. So here you have that CE to the KT showing up. So T sub F would be the final temperature T sub S is the temperature of the surroundings. So if you cooled whatever you had heated up down in a room of 75 degrees, that would be that temperature. And then C is the difference in initial temperature and T sub S. Okay, so the difference in if you took it out of the oven at 500 degrees and your surroundings were 100 degrees, that would be 400 degrees. Okay, the difference between the cooling temperature of the room that it's going to be cooled in and when you first began the cooling. Okay, so let's do our example of Newton's law of cooling. That's going to be number 56 on page 365. So 56 says, when an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. 1 hour after it was removed, the core temperature is 1120 Fahrenheit. Find the core temperature 5 hours after the object is removed from the furnace. All right, so here what we have an initial, so our final temperature is after 1 hour is 1120 degrees. So we need to get K. So you have 1120. The temperature of the surroundings is 90 degrees. So we're given this initial data that after an hour it cooled down to 1120. Plus, okay, for this problem, C is equal to the initial temperature 1500 minus the cooling temperature or the temperature of the surroundings. So that's 1410. So 1410 E to the K, and it took an hour to get to 1120. So this is kind of our initial data to form a model. So that one is 1 hour of cooling. All right, so we will subtract 90 from both sides. So that would be 1030 is equal to 1410 e to the k. K times 1, so e to the k. So if we divide both sides by 1410, all right, we're going to get 0.7305 is equal to e to the k. So let's take the natural log of both sides. So the natural log of 0.7305 is equal to k times the natural log of e, which is 1. So if you take the natural log of 0.7305, you will get that K is equal to negative 0.314. Okay, so our model, we want to know how long, what is the temperature 5 hours? So that would be T of 5. So that's going to be 90 plus 1410 e to the negative 0.314, that's our K that we just found, times 5. So we'll just put that into our calculator. All right, and that's 383.3 degrees. So that makes sense because we're cooling down after 5 hours. We started at 1500. After 5 hours of cooling, we are down to 383.3 degrees Fahrenheit. So our homework for this lecture starts on page 364. You can do 39, 41, 45, 47, and 57. So there you go, and I will talk to you on the solutions video.